Okay. So I want to say something about intuitive understanding of acceleration in 2D. This is pretty much the topic that we covered in lab last week, but this is going to be a big thing in the class, and I want to get it in your notes here. So I'm going to start by talking about acceleration in 1D, and then we'll extend that to 2D. So in 1D, acceleration means speed change, and that's the end of it. So if the object is speeding up, the velocity and the acceleration are in the same direction. And if the object is slowing down, the velocity and the acceleration are in opposite directions. So for example, if an object is speeding up as it rolls down a ramp, so let's say here's the ramp. Let's say the object is a toy car. It's going down the ramp. It's speeding up. So what can we say about the directions of the velocity and the acceleration? I'm going to draw the path of the car. So the center of the car, remember, is what we're treating as the location of the object. And that's following this green path. It's moving down the ramp, so its velocity is this way. And it's speeding up, so the acceleration is in the same direction as the velocity. So that's all that can happen in 1D. In 2D, acceleration means, so it can mean speeding up or slowing down. You know, it can mean speed change. But it can also mean turning. Because now in 2D, there's the possibility to change directions, not just change speed and whether you're going this way or that way. There's this whole range of directions. The speed change is affected by the part of the acceleration that's parallel to the velocity. And you can think of that as like the acceleration in 1D. And this new one is due to the part of the acceleration that's perpendicular to the velocity. And then the total acceleration is just the sum of these two parts. So let me write down some steps that you can think of to figure out what you can determine about the direction of the acceleration. So these are the steps for visualizing the acceleration in 2D. First, draw the object and its path in the real world. Second, now this is going to be easier now that you've drawn the path of the object. Draw the velocity vector tangent to the path and in the direction of motion. I'm going to first go through all these steps and then we'll do some examples and see how to use these. Third, is it speeding up or slowing down? If it is, if yes, then if it's speeding up, draw the part of the acceleration parallel to the velocity. A parallel is in the same direction as the velocity. And if it's slowing down, A parallel is in the opposite direction of the velocity. Number 4. Is it turning? And how can you tell whether something's turning or not? Well, if its path is a curve, then it's turning. If the path is a straight line, then it's not turning. So if it is turning, if yes, fit a circle to the path and A perpendicular is toward the center of the circle. And remember that A perpendicular always has to be perpendicular to these two other things you've drawn, the velocity and A parallel. Okay, they always have to be 90 degrees apart. And then the last step is the total acceleration is the sum of the parallel part and the perpendicular part of the acceleration. So if both of those are non-zero, then it's going to be a range of directions. If one of those is 0, it's just going to be in the direction of the other one. If they're both 0, there's no acceleration. Okay. So let's go through a couple examples and think this through. Okay, so let's say first that there's a ball rolling, and let's say the speed is constant. As the ball rolls to the right. Okay, I'm going to draw the path of the center of the object. So there's the path. And that green dot right in the middle is what we're thinking of as the object, because we're treating everything like a particle. The velocity is tangent to the path in the direction of motion. So there's the velocity vector. Is it speeding up or slowing down? No, the speed is constant. So that means there's no A parallel. So I'm not going to draw anything in there. Is it turning? No, it's following a straight line. And so constant speed, not turning. Let me write it as along a straight line. And so the acceleration is 0, which is another way of saying, in other words, the velocity is constant. Okay, so now let's go to some where we will have parts of acceleration. So let's say now that this object is slowing down as it rolls up this ramp. The path is this. The velocity is tangent to the path in the direction of motion. So here's the velocity vector. It's slowing down. So is A parallel in the same or opposite direction of V? It's in the opposite direction. So here's A parallel. Is it turning? No, it's moving along a straight line. So the total acceleration, if you go back up to this sum, we have something for A parallel, but nothing for A perpendicular. So A is just equal to A parallel. And so this is the direction of the total acceleration. Okay, and that's just a one-dimensional. I mean, this is something we thought of as a 2D problem, but it just reduced to a 1D problem because it's just moving along a line. Okay. Okay, now let's think of something moving along a circular path like this. And let's say that at this instant it's moving with a constant speed. This has a constant speed. Does it have a constant velocity?
No.
No, that's right. We're going to see that there is an acceleration here, and anytime there's an acceleration, it means velocity is changing. Okay. The velocity is tangent to the path in the direction of motion, so like this. Let me draw that a little better. Okay. The speed is not changing, so there's no part of the acceleration parallel to this. It is turning, and if you fit a circle to this curve, that circle would be down below the object. And so A perpendicular is like this. And the total acceleration is the sum of A parallel, which is 0, and A perpendicular. So this is just equal to A perpendicular. So there is acceleration. So velocity is not constant. So if the speed is constant, how can the velocity not be constant? How can the velocity be changing? The direction, exactly. Remember that velocity is a speed combined with a direction. And if either of those change, the velocity changes. Okay, so now we'll get to the deluxe model that has everything in it. And let's do this one for projectile motion problem. So let's say that the object is following a path like this. And let's say we want to analyze what's happening to the object over here. Okay, so I'm going to draw something first. We know a lot about projectile motion. We've spent a lot of the class so far talking about projectile motion. So based on what we've been doing before we started thinking about 2D acceleration like this, what do we know is the acceleration of something in projectile motion? Yeah, right. And I'm just going to draw the direction, but it's just straight down, right? We know that's the acceleration. But now we're going to take a different approach. Excuse me. And we're going to draw the velocity, parallel part of the acceleration, perpendicular part, and come up with a range of possible directions. And what we need to see is that this downward acceleration that we know is going on, it better fall in our range of possible accelerations with the other way of thinking about it, or else something we're doing is wrong. You know, they have to agree with each other. Okay, so the velocity is tangent to the path in the direction of motion. So there's the velocity. Is it speeding up or slowing down while it's on the way up? Slowing down. And so A parallel is like this. Now, if you fit a circle to that curve, it would be on the underside of this curve. And so the perpendicular part of the acceleration is this way. Now, the total acceleration is the sum of these two. So we're going back to adding two vectors where we don't know the magnitudes, but we know the directions. And so we know that the range of directions for the sum is this. And you can see that that gray arrow that I drew before I started this analysis, that downward arrow falls in that range. So that's sort of your question about the labs. The idea is you're thinking about it two different ways, and if you're thinking about it right, they have to agree with each other. Any questions about 2D acceleration before I go on? Okay. Well, the next topic we're going to get into is 2D particle kinetics. We've been doing kinematics. So the next topic, 2D particle kinetics. And so remember that the meaning of all this, 2D means that the object is moving in a plane as opposed to a line in 1D. Particle means the object is treated as having mass but no size. And now kinetics combines kinematics. So we're going to keep using all of the kinematics that we've used up until now. But now we're going to introduce the causes of the motion. So it combines kinematics with the causes of the motion. And those causes are mass, force, and energy. We'll talk about energy a little later on. For now, we're just going to be dealing with mass and force. And so before I can get into the big equations for doing kinetics calculations, I have to define these new terms. So first I have to define mass and force. Okay, so the first new term that we have to define is mass. And the thing I want you to keep reminding yourself is mass and weight are not the same thing. So weight is the force that gravity applies to an object, and mass is, what we're going to define right now. There is a relationship between mass and weight, and bathroom scales usually have settings on them underneath where you can flip between measuring mass and measuring force, but it's not the same thing. A bathroom scale actually, we'll talk about this, we'll put some numbers in it and stuff, but a bathroom scale doesn't actually measure mass. It measures the force that the scale is applying to your feet. Well, if it's reasonable for a bathroom scale manufacturer to assume that you're using this scale on the surface of the earth, then it's simple math to switch from the weight, the force that the scale's applying to you, to your mass. But it's not the same thing. And if you took a bathroom scale to the moon and had it on the setting for force, it would measure that force accurately. If you had it set on mass, it would measure your mass inaccurately because it's making false assumptions. Okay. So weight is the force applied to an object by gravity. And so the key is weight is a force. Mass is not a force. Mass is mass. That's all it is. And so how do you measure mass? Well, mass is a measure of an object's resistance to acceleration. So for example, if a bug is flying by and you swing your hand and hit it, you change its velocity pretty drastically over a pretty short amount of time, right? Pretty easily you can swing your hand and cause a big acceleration in a bug, okay? Now think of doing the same thing with a semi-truck, and it would take a very sensitive measuring device to measure any change in the velocity at all from your hand, okay? That's because a bug has a very low resistance to acceleration, and a semi-truck has a very high resistance to acceleration, okay? So you see this in football a lot. Okay, so here's a football drawing. This is one football guy. Okay, there's one guy. And he's about to collide with another guy who looks like this. Okay, so when they collide, one of these two players is going to accelerate very drastically, and one of these players, if his eyes are shut when they collide, he won't even notice that this collision happened. He'll just keep running with this other player attached to him. You know what I mean? And so in this collision, there's going to be a very low acceleration for this guy, a high acceleration for this guy. And that's because this guy has a big mass, a big resistance to acceleration, and this guy has a low mass. Okay? So if you apply the same force to two different things, the one that accelerates more has a smaller mass, the one that accelerates less has a bigger mass. Okay. The SI units. So usually I say like, okay, what are the units, and then what are the SI units? Well, mass has its own units, and so I'm just going to tell you what the SI units are that we're going to use. And it's kilograms. You might think it makes more sense for it to be grams because there's no prefix, but this is just what it is. And mass does not have a direction. So mass is just a positive number. Not a vector. And what that says is that there's no direction associated with mass. This idea of mass being a resistance to acceleration, when people are like on, living for a while on the International Space Station, it's a real concern that they're going to lose muscle mass and lose bone density. And so they want to be, like the doctors want to be monitoring their mass very carefully. The problem is when you're in orbit, there's no apparent gravity, so you can't put them on a bathroom scale and use that to measure their weight and then calculate their mass. So what they do instead is they use this idea of resistance to acceleration. They put them in a machine that applies known forces to them, and then it measures their acceleration according to, it's like, and if they're accelerating a lot, then their mass is down. If they're accelerating a little, their mass is up, and they can do those calculations. But you can't measure weight without gravity. So in orbit, a bathroom scale says 0 no matter what your mass is. Any questions about mass or about what position this little football player plays? Probably punter. Okay, and then the next thing that I have to define is force. Mass was just a number. Force is a vector. Force is a vector that measures the intensity and direction of a push or pull. The units of force are pretty messy. The units of force are units of mass times units of length divided by units of time squared. And so the SI units for force are kilogram meters per second squared. Okay, sounds good.
Length and time squared this acceleration.
Yeah, right. That is, you'll see where that comes from when we get to the big equation in this section, yeah. And we're going to use force all the time, and this is kind of a cumbersome set of units to keep writing down. So we're going to give this its own name. So 1 kilogram meter per second squared is equal to 1 Newton. So we're going to think of Newton as our measure of force in SI units, and we're going to abbreviate it with a capital N. There are only 4 types of force that we're going to see in this class. That's going to help sort of simplify problems when they start looking kind of complicated. So there are 4 force types in this class. The first one is the weight force. And like I said, that's the force applied by gravity. And then there's a second category that has 3 types, 3 individual ones. This category is called contact forces. So gravity applies force to things without touching it. These contact forces have to be touching the body to apply a force. And they are a pushing contact, a pulling contact, and this pulling contact, in parentheses, I'm going to write cable next to it because when something's pulling on another object, we're going to always think of replacing that contact with like a string or a rope, a cable. And then the third one is friction. So whenever a force is acting on an object, your job is going to be to identify which of these 4 types it is and then follow the rules for what you know about that kind of force. Okay, and each one of these will have its own rules associated with it. And then what we're going to get to, the big equation, is Newton's second law. I'm going to abbreviate it N2L because I'm going to write that a lot. And this is the equation. So first, before I say that, this is the most important equation in this class. And notice that it relates the mass, force, and the acceleration. So it's kind of like our way to get from these causes of the motion to the actual motion, which is the acceleration. And you've probably heard this sometime or other. This is F equals ma. In this class, we're going to be a little more careful about what it means. So I'm going to write it as F net, the vector F net, is equal to the mass times the acceleration of the object's center of mass. So this is it. Where F net, this vector F net, is the sum of all the forces acting on the chosen object. M is the mass of the chosen object. And ACOM is the acceleration of the chosen object's center of mass. So I said this is the most important equation in this class. When I was in high school, I took AP Physics. I think I was a senior. And our physics teacher said, without knowing anything about physics at all, if you wrote F equals ma on every problem, you would get a 3 on the AP test. I'm very skeptical about that. I didn't try it. I didn't take the AP test because I didn't feel like I'd learned anything. But anyways, that's his opinion of how important this equation is. And so the next thing I'm going to do is I'm going to use this equation. So we have these 4 force types that we have to figure out how to deal with. The first one we're going to go into is the weight. So how do you know an object's weight? And we're actually going to figure this out from Newton's second law. Okay? So now I'll use Newton's second law to determine the weight force on an object. And as I do this, just for like a notation to simplify writing stuff, I'm going to define this lowercase g as 9.81 meters per second squared. So you could write that in different units if you did a conversion. You know, you could write it in feet per second squared or whatever. But that's what g is. And let's think about a 1 kilogram object in free fall. Since it's in free fall, it's not touching anything, right? So if you look at these type of forces, it doesn't have any contact forces on it. The only force on it is weight, the force applied by gravity. And do we know what its acceleration is? We've been talking about this a lot, right? Projectile motion and free fall. Yeah, we know that its acceleration is 9.81 meters per second squared down, or we could also write it as an acceleration of g, 1g down. Okay. So now I'm going to use Newton's second law. With the y-axis of my coordinate system pointing up. Okay. And Newton's second law says add up all the forces acting on the body. In this case, all it is the force, the weight force. And that's equal to the mass of the object, which I said was 1 kilogram, times the acceleration, which is 0, negative 9.81. And so the weight force is 0, negative 9.81. If you multiply kilograms and meters per second squared, you get newtons. So this is in units of newtons. So that's the force that gravity applies to a 1 kilogram object. You think gravity applies the same force to everything? Or, okay, so this is where you got to think through a little bit of complexity. So I spent a lot of time telling you that every object, no matter what its mass was, fell at the same rate, right? If there's no air resistance, and we're going to forget about air resistance for now. What am I saying? Right. So no matter what the masses are, any two objects fall with the same acceleration. But objects with different masses are pulled on with different forces by gravity. The thing is, like, think of a feather and a bowling ball. To get something as light as a feather to accelerate at 9.81 meters per second, it's not very resistant to acceleration. So you don't need a very big force to pull it down, you know? Whereas a bowling ball, it takes a lot more force to get that to accelerate at 9.81. And so even though any two objects, no matter what their masses are, accelerate down at 9.81, the forces are bigger as the mass gets bigger. And the forces that are applied just happen to be exactly such that the accelerations of everything is the same. Okay, so so now let's do this same thing for something bigger. Let's do 100 kilograms and see what happens. So now we're going to do a 100 kilogram object in free fall. So Newton's second law says the weight force acting on the object is equal to the mass, 100, times the acceleration in free fall of negative 9.81. And this time we get a weight force that's equal to 0, negative 981 newtons. So even though the accelerations are the same, the force on the 100 kilogram object is 100 times the force on the 1 kilogram object. Okay, so now let's just do it one more time. Generally, where the thing has a mass of m instead of like a numeric value. So now one general case, this is for an object with a mass m that's in free fall. So Newton's second law says the weight force is equal to the object's mass times its acceleration, 0, negative 9.81. And so you get that weight force is equal to 0, negative 9.81 m, or you often see it written as 0, negative mg. Okay, so whatever the mass is, you multiply it by the free fall acceleration of gravity, and that gives you the force that gravity applies to the object. Okay? So mg acting down. This is the force gravity applies to an object no matter what the object is doing. Okay, so an object, like a 1 kilogram object sitting on the table, gravity is applying a downward force of mg. That same object, if you drop it off the table, gravity's pulling just as hard on it as it falls. That never changes, okay? So now that we've figured this out, let's think about what happens when you stand on a bathroom scale. Like how does a bathroom scale measure your weight? So let's do this as an example problem. How does a bathroom scale measure weight? So let's say that there's a scale on the floor and a person on the scale. Let's say the person has a mass of 100 kilograms, just to make the calculations easy. Okay. And the scale, there's no way for the scale to directly measure the force gravity applies to the man. Okay. But what the scale can do is measure the force that the scale applies to the man. So that's what we're going to figure out. What's the force applied to the man by the scale? Okay, well, there are only two forces acting on the man. There's the weight. Anything with mass has weight acting on it. And then you have to think about contact forces, and there's only one place that the man is making contact with anything. That's the scale. So the only other force acting on the man are the force applied by the scale. Okay, So let's put these into Newton's second law and see if we can calculate the force that the scale applies to the man, okay? So Newton's second law says, well, there's a weight force, and we know what that is now. That's equal to 0, negative 981. This is the weight. And then there's a second force that I'm going to call Fs, the force from the scale. And I'm going to break it up into its components. So we have Fsx and Fsy. This is the force from the scale. Now, these are all the forces acting on the man, so now we can say this is equal to the man's mass, 100 kilograms, times the man's acceleration. Okay, so what's the man's acceleration? He's not in free fall, he's just standing there, not moving. So his velocity is 0, and his velocity is just staying 0, so the velocity isn't changing. So what's the acceleration? 0. Because the velocity is constant. Okay. And now I'm going to think of this as two separate equations, an x equation and a y equation, to calculate those components. The x equation says 0 plus Fsx is equal to 100 times 0. So 0. And this tells us that Fsx is equal to 0. And then the second equation says negative 981 plus Fsy is equal to 100 times 0. Do the algebra on that, and you get that Fsy is equal to positive 981. And so if you put these together, what we get is that the force vector from the scale is equal to 0, 981 newtons. And so the scale feels that it's applying a force of 981 newtons. That's what reads on its screen. And as long as the person isn't accelerating, and as long as the person isn't touching anything other than the scale, that shows the person's weight. Okay, but you know, like if the person got on the scale and leaned hard on the sink as they're on the scale, then there would be a third force that would have to go into Newton's second law, and that scale force would not represent the weight anymore. And you sort of know that intuitively, you know. You can be like, look, I weigh 20 pounds, you know. Okay, let's do one calculation of what happens if the person is accelerating. So let's imagine, for another example, that a person is has the scale on an elevator, okay? And
Are you ever going to give us weight in pounds?
no. But it's about 1 Newton is about a quarter pound. So you can sort of get a sense of it from there. So this person weighs right around 1,000 newtons, so 250 pounds. And when an elevator starts to move, right at first, as it goes from 0 velocity to whatever its velocity is going to be as it goes up the 5 floors or whatever, there's a short time where it's accelerating to get up to its final speed. And during that time, it's accelerating. So let's say that the elevator is accelerating down at 2 meters per second squared. What's the force applied to the man by the scale? Okay, this is just like a quiz. If the elevator is accelerating down at 2 meters per second squared, does that mean that the elevator is moving down? Not necessarily. There's two things that could be happening. If it's moving down and its acceleration is down, is it speeding up or slowing down? Speeding up. If it's moving up, it can still be accelerating down. What would be happening in that case? Slowing down. That's right. Okay, so here's what's going on. So here's the elevator. And the scale is on the elevator. And then here's the man. I like his outfit. And the elevator is accelerating down at 2 meters per second squared. And so Newton's second law says we have the weight force. If it's the same man, it's still a weight force of 0, negative 981. And then we have the force of the scale acting on the man, so Fsx, Fsy. And then that's equal to the mass of the man times the acceleration. This time the acceleration isn't 0. It's, what is the acceleration vector? So here's our coordinate system. Put the tail of the vector at the origin. What are the coordinates of the head of that vector? 0, 2. Yep. So this is 100 times 0, negative 2, sorry. Because it's, negative y coordinate. And so we have the two equations again. The x equation says 0 plus Fsx is equal to 0. So Fsx is equal to 0. And the y equation says negative 981 plus Fsy is equal to 100 times negative 2, so negative 200. And if you do the algebra on this one, you get that Fsy is equal to 781 newtons. And so this vector Fs is 0, 781. So just for this half a second or second that the elevator is accelerating, the scale would suggest that the man's weight dropped by 200 newtons. Okay? The weight didn't really drop, but what a scale does, all it can do is calculate that force that it's applying to the person, and that force has gone down. Any questions about that? Okay, let's stop there, and then next time we'll start doing all those contact forces and talking about how to treat those.